Thank you for the invitation, and happy to present the work done with Bernard Armand of Macquarie University in Sydney. And we have presented this work in the blockchain workshop in Infocom. And so the starting point of my presentation is the remark that the Bitcoin, it is something that is known since long, is wasting a lot of energy because of the proof of work. And the quantity of energy is 40 gigakilowatt hour. So gigakilowatt hour is 1,000 times a gigawatt, or maybe it's a gigawatt. So it is like the energy consumption of a country like Greece. I don't say that all Greek people are doing mining in Greece, but it is considerable. 6% of France is 0.25% of the world. It's not still that big, but it is not negligible. And the reason of that is the fact that each block miner, we have also see what is a block, how it is mined, how there are ambiguities, how it can be solved. But before mining, in the current description of the protocol, each miner must find a hash value which has 74 initial zeros out of 256 bits. And the difficulty, it is called the difficulty. The difficulty has another definition, but basically this number of zero is called the difficulty, and the difficulty is adjusted in order to have in average one block every 10 minutes. And for that, every miner adjusts this small field of 256 bits and try to find the value which will give 74 zeros. And there is no known way that trying the random values until you reach this number of zeros. The evolution of difficulty, the reason why the difficulty is becoming more and more difficult is because there's more and more people competing for mining. And this, I don't know if this curve has any meaning. I took it from the web, and basically it gives you the increase of difficulty in terms of processing power during since 10 years, and you see that difficulty is increasing dramatically. And in parallel, there is the value of the Bitcoin, and some people want to see some relation, but it is not my problem here. What I wanted to show is that basically the difficulty is tending to increase and to, consequently, to have more impact on the energy. So the alternative to the proof of work, PO means proof of work, is what I'm suggesting in this presentation, is the block mining via inversed leader election. So the inversed leader election looks strange. This is a leader, which is known in France. And in general, what you do is a leader election. You do like an election, but in this case, the strongest has to win. So all competitors compete, they try together and assume that half of them survive. And after several steps, the survivors, which survive at every step with probability P, therefore, until the Lth step, it will P to L probability to survive, the number of competitors decrease until you reach the no survivors. And those who survive the previous step are those who will be allowed to mine their block. You will tell me, no, you won't tell me because I will tell you before you tell me, is the fact that it is very expensive. It means that if you have 1 million blocks in competition, they all have to contend to detect there are too many, and then to content again, content will be the waste of energy again for the access to the depository. So the idea is to do the reverse election, leader election. The reverse leader election, basically you start with a very low probability to survive, and you increase this probability until you have survivors. In this case, you will have empty slot until you have a slot which is not empty, and you stop here. It will be the election. The question is how many in average will survive. If there are a lot, then we lost our game. If there are less than one, no, the idea there will be more than one. But if there are, say, 4, 10, something like that, even if the number of the initial contender is huge, then we win our bet. The properties of the reverse leader election is when we define a number k, which is the maximum number of phases for the leader election you accept. Because if you start from the end, you have to know in advance the maximum number of steps. If you start from the beginning, it is open. But if you start from the end, you have to know the maximum number of steps. If P to K is P to minus K is something which is much larger than the number of contenders, then the number of blocks mined per election is bundled in distribution by some numbers, which is some A times N, the maximum number of contenders, to 1 over K. So if N is the order 10 to 9, if K is the order of 10, then you see that you will you won't have too many blocks at the end. And the factor, in fact, is of this order. I'm not going to describe how we arrive to this order, but basically, if you try n equal 2 to 32, which is basically a huge number, but not necessarily completely unrealistic. Therefore, if you are afraid by 2 to 32, take 264. Then n k equals 16, then you will have less than 4 mine competition at the end. Of course, there is a miracle if you are above the maximum eligible number accepted, larger than 2 to 32, therefore your number of blocks will increase linearly. What is interesting in this scheme is the fact that big capital N and P are fixed as initial parameter. You assume, for example, if you are very shy, you just say that N is the number of particles in the universe. Therefore, you'll be sure that the number of blocks in some nursing farming in a remote place in Antarctica will be smaller than 10 to 80. And it is fixed at the very beginning. There is no need to review and update every 2016 blocks, which is an average 2 weeks. The current protocol readjusts the difficulty by consensus, difficult consensus by the way, by updating this difficulty value every 2016 block. Why 2060 blocks? I don't know. It's a nice number, but it's average, in average 2 weeks. So this is the regular block for the green mining format. As you can see, there is no nonce value anymore. So one thing less, and there is one additional field, which is the next block call value. The next block call value will tell you basically that you will accept only the block for whose hash value will be smaller than the next block call value. For an irregular block, it is fixed by protocol to be 2 to 256 over n. So it's a big number, but it's in fact very small number compared to 256. So it's almost impossible to have a hash value of this value, but it is the starting point. And the next regular block should have hash value smaller than this value. Of course, you will tell me that with n equal to 32, the difficulty is not very big. But don't forget, there's no nonce to tune anymore. There is no way to adjust the hash value of your block. The only way to adapt the hash value is to modify the transaction reference. And the transaction reference are made by a Merkle tree. And it's complicated. You have to import a reference to take its hash value to modify the Merkle tree. It's less easy than to increment the nonce value. So it's more difficult. At the very beginning, it's virtually impossible to have an hash value smaller than this initial call value. So after 1 minute, I assume it's 1 minute, an empty block is inserted with a higher hash value. And every time, and if there is no regular block mined with, I will say, the suitable hash value, you will increase the hash value until blocks are coming. So the empty block, which is the novelty of the thing, it's smaller. It's like a regular block, but without any transaction. It's just to tell that you will increase the call value. If the no regular block is mined, a new empty block is mined with call value larger, with, you just multiply by p2-1, and the process, you can do that k times, because above k you will have a hash value will be smaller than 1. You restart until you have a regular block incoming. So one example, this is the first call value, the second call value. You see the call value increase, and at the end, in case we are very unlucky, or in case nobody has anything to mine, and it may happen, by the way. Apparently, it is not the current tendency. This is the final value, the call of the hash, the call value. So the last call value releases all blocks if there are all blocks, a lot of blocks. So the empty block, there are many options. One option is to have a central entity with a secure depository. Nobody likes it. Why not? It is simple. And we'll take 1% of value for every mining, so you'll be very rich. It can be mined in the centralized mode to be filtered by block dates. Since the value of the empty block is expected, there is nothing new. You may have several empty blocks, they will be all the same, you just keep only one, that's all. You can do also implicit empty block mining. Basically, instead of displaying an empty block with a larger call value, you know the protocol, you know that after 1 minute, the call value could be increased by a factor 1 over p, and you just basically make the filtration via the date. Performance analysis. Because, of course, yes, it is still not too late to have ugly formulas. So there is a closed formula for the average number of empty blocks. This is this formula. The proof, I'm not going to describe the proof. The proof is basically the probability that the process reach around L is this quantity. It means that you must first have failed the first round. There should have been no blocks with the expected hash value before. And after, this quantity you see that it's just of the order 1 over p, and 1 over p is, since after k iteration you arrive to from n to 1, it is of the order n to 1 over k. Therefore, you have the proof that the average number of mined block is of order the maximum acceptable number of blocks in competition to the power 1 over k. And this makes a drastic reduction. You have also if you have implicit empty blocks, the difference between the explicit empty blocks is the fact that every time you mine an empty block, you basically change the hash value of the next block, which must refer to the previous block, and therefore the hash value of the next block is, in the model, completely independent of the hash value of the previous block. If you do mining with empty implicit blocks, you don't change the hash value of the blocks because you always be attached to the first regular block. And the consequence of this is not very important, but the fact that the proof that we have this quantity, the probability to reach each round is this quantity instead of the product we have before. Because in this case the probability adds. Before they were just a product, but now since it is not they are not independent event, the probability adds. You could ask me, but is implicit or explicit empty blocks, which one will give the best result? In fact, none. In green it is explicit, and in red it is the implicit. And maybe it is the reverse, but I forgot. And you see that one can be larger and the other can be larger. This is oscillation.
Why do you have the ripple?
We have ripple because this formula, basically, if you to analyze it, you will see that it's like a Dirichlet theory. If you want to make the analysis, it's like a Dirichlet theory, and a Dirichlet theory that you can treat via Mellin transform show periodic fluctuation.
And why in the end does it go up?
Because you are close to the case when you are close to the maximum number is 10 to 9, then the factor n times p is going to take the lead. The linear part will take the lead. Here, for doing this analysis, you forget this part, which is linear. You got something which is periodic, and then to complete the analysis, you introduce this linear part, which is not important as long n is not close to the maximum, which is 10 to 9 in this case. It will be 10 to 20 if we take 2 to 64 instead of 2 to 32 as the maximum number of expected block in competition. What is it? This I don't remember. Yes. It's good to have the average number of mined block, but sometimes you may say, okay, he's telling us that in average it's just 2 blocks, but maybe sometimes this is 1 million. And so is it possible to have an idea of the distribution of the number of mined block? And this formula gives you the distribution. And you can play this formula to find this limiting distribution, which will be an oscillation, to see that it has exponential tail. It has an exponential tail, so it has a good behavior. And but which is more funny, at least for me, not for you probably, but for me, this is very funny, is to make the simulation of the system. It is not difficult. And this gives you, for each number, not each number one by one, for numbers between 10 blocks and 1 billion blocks, And I tried several times, and I tried to know how many blocks are mined per session. And the black points mean that it's points that have been attained 64 times during the simulation. I did only 100 simulations because I'm lazy. Red, it is, I don't remember, 16, 4, and this 1. So it can go up to 20, even close to 30 in the simulation, because the limiting distribution, the distribution may not have any limit, can be n, can be very large. But it is very, very unlikely to be n, extremely unlikely. The conclusion, just a repetition of what I said at the beginning, that energy waste due to the proof of work is not sustainable in cryptocurrency. It's currently it's the cost for mining a Bitcoin. There are many Bitcoins per transaction per blocks. Is tending to be close to the value of the Bitcoin. So at some moment, it won't be it won't be good. And you can see if you have with the actual protocol where you try to adjust the difficulty with the number of contending nodes, basically the energy consumption is increasing between something linearly or quadratically with the number of contenders. So it's something which is going to be not to be sustainable with the future. Here we describe the reverse leader election. That replaces the burden of the proof of work for mining difficulty. It is highly dynamic, work for any mining population up to n, arbitrarily large, no need of parameter update. In fact, it could be adapted to something that is called the kernel of proof of kernel. The proof of kernel is, in fact, it's a proposal, but there is no algorithm, is how to thin the population of contending blocks so that a small set will actually process the proof of work. Because the proof of work is in fact needed for other reason, that is to make difficult the entire rewrite of the blockchain by an adversary. So we can introduce the nonce again, but without this increasing quadratic difficulty. The perspective. The big question with this scheme is how it is resilient to attack. Because it's nice, it's a lot to avoid the proof of work, but how it is resilient to attack, because somewhere there are people who want to attack. They love attacking, meaning in cryptocurrencies, they want to attack it. We can replace what we have currently. We have a lot of proof of work farming. What is proof of work farming? Basically, it's a guy, in general it's a company who has a lot of computers, lot of cluster of computation, and they are in parallel computing, incrementing the hash function until you reach the actual difficulty. And this is the reason why it is so expensive, because there are people who try to take the lead on the currency, and the classic attack is called the 51% attack. The 51% means nothing. It's just basically to say that if you want to gain epsilon over an adversary, which mean you have to put in the stack in order to get this epsilon. And this, it turns out, via very simple analysis, because it is not yet completely achieved, that the quantity of means you have to add will be of the other 2 epsilon log over 1 p. So if p is small, but the logarithm is not going to make something big, then basically you have to pay a penalty in order to be epsilon stronger than the adversary. But in this case, you have to modify the proof of work farming, all this computer working independently, by the block nursing, which is a little more complicated because block nursing you have to take all the transactions to build the Merkle tree to recompute the hash function because there is no other way to change the hash value of the block than changing the content of the block. So that's the future work. That any equation, there was a slide written with question, but apparently for economical reason it is not there. Thank you.
The Bitcoin is known to be very consuming in energy, but there are other Bitcoins, I think like Ethereum, that are less consuming. So do you...
I don't know well there are proposal, but actual cryptocurrency using something else that's a proof of work, I don't know much. There are proposals, but things that are really implemented that I don't know.
There's a few proof of stake, proof of other things like memory, or so they are implemented. Like Ethereum is using proof of stake.
There is a proof of kernel that I know, but it is the way to do the kernel is open. It's just a proposal. Find a way to reduce the contending population.
There is another question.
Did I understand correctly? In fact, you don't completely remove proof of work, but you choose leaders by starting with a very high difficulty and then decreasing it every minute, right?
No. For this, to simplify, I remove the proof of work and just every contender has his block ready. The block has a hash value, and there is no way to change the hash value.
Oh, there's no way. But still, there are ways to change your hash value. You can shuffle transactions or change the transaction that you put in there.
Yes, but
it's validate the block. So
yes, but it's very expensive. It's very expensive, but doable. But I mean that in this case, at least only the people who want to fool the system will spend a lot of energy. The other, at least, there was a presentation in Infocom and said there is the miner and the honest miners. There was difference between the honest miners. Yeah.
So the question is, first is that the performance analysis is on expectation. Is an expectation the performance analysis?
It's an expectation and a distribution also.
Exactly. So wouldn't it be more interesting to see also like higher moments of this? Because
Yes, it was what I presented.
You have?
Yes.
And then the second
It was a nice picture.
I see.
I was very proud of it. So very sorry that you didn't notice it. Wow.
Like, what is the motivation for the fixed pay, for the fixed probability P?
What's the motivation to have it fixed?
Exactly.
The motivation is not to have to change it.
But,
Not to have to change it.
but why? Why not change it? Why not make it?
Because, I will give you the political reason, because changing parameters in a protocol needs a consensus, and sometimes this consensus is not that easy to reach, and that's the main reason. And you don't need it for that. That's also the other reason. It's a less political reason that you don't need it for this protocol.
I have a question about how do you get consensus on time? So what's the 1 minute
A good question. I don't have the answer. You should assume that you have a source of distribution of time which is enough reliable.
Yeah.
There is a Unix, the source for Unix, but which is okay for the minute, I think.
Yeah, but the problem is that you are in a distributed system where nobody trusts anyone, as Maurice has kind of suggested at the beginning. So if we had time, then you could have some sort of submission, and then there is someone who says time's over, and you pick up the submission. You wouldn't have to do anything.
I did not investigate too much this aspect, but you must have basically the time where you receive the block and the time the block is claimed to have been created.
Yeah, but the problem is who is you, because there's many yous, and it's